Right now, in the room you're sitting in, there is a tiny piece of metal, thinner than a human hair, being heated to over 2,000 degrees Celsius, hotter than lava, hotter than the exhaust of a jet engine. And somehow, it isn't melting. It isn't burning. It's just glowing. Quietly, for 1,000 hours straight, that object is sitting 2 feet above your head. And almost nobody on Earth knows how it actually survives. By the end of this video, you'll understand the exact engineering trick that lets a bulb run hotter than the surface of some stars without instantly destroying itself, and why it took almost 40 years to figure out. We are going to open this thing up completely, cut it in half, trace every wire, and by the time we're done, you'll never look at a light switch the same way again. Here's the basic idea, and it's beautifully simple. If you push electricity through a wire that resists the flow, the wire heats up. Push it hard enough, and the wire gets so hot, it starts glowing. First dull red, then orange, then a brilliant white. This is called incandescence. The same thing happens to a metal rod in a blacksmith's forge. The bulb is just a forge, shrunk down and made safe enough to sit beside your bed. But here's the catch that stumped inventors for decades. Any normal metal, iron, copper, even steel, will burn up in seconds at those temperatures. Especially in open air, where oxygen reacts violently with hot metal. So the challenge wasn't making something glow. That part was easy. The real challenge was finding a material that could glow white hot for hours, even months. For most of the 1800s, inventors tried everything. Platinum, carbon, even bamboo fiber. Baked until it turned to pure carbon. Edison's team tested over 6,000 materials, settling on a carbonized cotton thread that could glow for around 40 hours. But 40 hours wasn't good enough for a world that wanted electric light in every home. The real breakthrough came with tungsten, the highest melting point of any metal on Earth. The real breakthrough came with tungsten, the highest melting point of any metal on Earth. You cannot bend it into a coil. In 1910, William Coolidge at General Electric finally cracked it. He developed a process to make tungsten ductile, flexible enough to be drawn into thin wire and wound into a tight coil, like a microscopic spring. This single innovation is the reason almost every bulb made for the next 100 years used a tungsten filament. But tungsten alone wasn't enough. Even tungsten, at white-hot temperatures, will react with oxygen and slowly evaporate, drifting away and coating the inside of the glass with a dark film. Watch an old bulb burn out, and you'll often see that black smudge near the top. So, engineers had 2 choices. First, remove the air entirely, seal it as a vacuum. In a vacuum, tungsten atoms still boil off the surface and drift away unopposed, like steam with nowhere to push against. The second, smarter solution came in 1913. Irving Langmuir filled the bulb with an inert gas, usually argon. These gas atoms don't react with tungsten, but they create an invisible cushion of pressure. When a tungsten atom tries to evaporate, it collides with gas and is knocked back. The filament evaporates more slowly. The bulb lasts longer and can run hotter and brighter. Flip the switch and electricity flows in through the metal screw base. It travels up a support wire, through the glass stem, into the tungsten coil. As electrons collide with tungsten atoms, that energy becomes heat, the engine of the device. At 2,500 to 3,000 degrees, the filament emits radiation, most of it invisible infrared. Less than 10% becomes visible light, the warm glow you actually see. Hit subscribe Next time, we'll crack open another hidden machine together.